Welcome to part A of Lecture 2 of Introduction to Quantum Computer Systems. We will begin today's lecture by revisiting some of the concepts from previous class, but define them more rigorously. In particular, we're going to talk about the first two out of the four principles of quantum computation, namely superposition and transformation of quantum states. Next, we are going to try to understand properties and structure of a qubit by looking at its geometric representation, namely the Bloch sphere. And lastly, we're going to introduce the concept of quantum gates and quantum programs. So, what is the state of a qubit? As a review from previous class, a qubit is a quantum register storing one bit of quantum information. And what makes a bit of quantum information unique is that it can be in a state of a combination of 0 and 1. This combination is called superposition. And we can write down a quantum state as a linear combination of zeros and ones with coefficients alpha and beta that are complex number, satisfying this normalization constraints. So what is it really from a programmer's perspective? Well, it's just a data structure that stores the two numbers, alpha and beta, well, they're complex numbers. And later we'll see it is convenient to write them down as a vector, alpha and beta. Now, having two complex numbers are really difficult to reason about. A very convenient tool is to represent a qubit state in 3D space. And for this slides, we'll see why that is possible. Why can we represent a qubit in 3D? Well, to do that, let's take a quick review of the two coordinate system for a ball in 3D space, the Cartesian coordinates and the spherical coordinates. If we annotate this ball with the Cartesian coordinates, then we can see this is the origin. And we have the x-axis pointing to the right. We have the y-axis pointing inwards. And we have the z-axis pointing upwards. So any point on the ball, for example, on the surface of the ball, can be represented by their coordinates, x, y, and z. One can alternatively represent the point by its spherical coordinates. Let me annotate this figure further. We can represent a point in the 3D space by three other parameters, r, theta, and phi, where r is the distance from the origin. Theta is the angle between the z-axis, and phi is the angle from the x-axis. For a unit ball, namely a ball with radius 1, any points inside or on the surface of the ball needs to satisfy this relation in the Cartesian coordinates and respectively a set of relations in the spherical coordinates. Now, why do we care about the spherical coordinate of a unit ball? Well, this is because we can in fact rewrite a quantum state in those parameters. In other words, if we have a quantum state alpha 0 plus beta 1 that uses two complex numbers, we can rewrite it into these parameters. Okay, let's see how we can do that. We're going to use two facts. Fact one, global phase doesn't matter. In other words, we cannot distinguish a quantum state psi with another quantum state that is psi multiplied by a constant phase. As a result, we can in fact multiply the state with the phase so that the first complex numbers become a real number, and the second one is still a complex number. The second fact we're going to utilize is that alpha squared plus beta squared is 1. As a result, we can rewrite the quantum state without losing any information using this formula. Now we can, in fact, represent a quantum state with two real numbers, theta and phi, where theta is in this range and phi is in this range. Now, if we set r equal to 1, this means psi is on the surface of the unit ball. Now let's just try to locate some of the common quantum state on this Bloch sphere. So where's the quantum state psi equals 0? Well, for 0, we have r equals 1, theta equals 0 because cosine 0 is 1, sine 0 is 0, and phi is also 0. So we can pinpoint the state 0 on the Bloch sphere up here. Similarly, we can find the quantum state 1 by their coordinates, r equals 1, theta equals pi, so that cosine theta over 2 is 0, sine theta over 2 is 1, and phi equals 0. So 1 is all the way down here, the south pole of the Bloch sphere. Let's do one more example. What is the quantum state psi equals 1 over root 2 0 plus e to the I pi over 4 times 1 over root 2. Well, we just need to find the theta angle that gives us 1 over root 2, and that is pi over 2, and the appropriate phi equals pi over 4. So where is it on the Bloch sphere? That's right, it's in the xy plane, and in particular 45 degree from the x-axis. Another benefit of this Bloch sphere representation is that now we can understand transformation of quantum state or quantum gate, namely from one quantum state to another, as rotations of the Bloch sphere. So what are some examples of such quantum gates or transformations? Well, a valid transformation maps one quantum state, alpha 0 plus beta 1, to another quantum state, alpha prime 0 plus beta prime 1. They both need to satisfy the criteria to be a valid quantum state. So I'm writing down three simple examples here. Now let's use the Bloch sphere representation to visualize these transformations. First example, we want to map from alpha beta to alpha minus beta. So in this Bloch sphere representation, alpha is cosine theta over 2, beta is e to the I phi sine theta over 2. So we can write down this output state as this. Because we know that e to the I pi is minus 1, we can rewrite this quantum state now as cosine theta over 2, 0 plus e to the I pi plus phi sine theta over 2, 1. So what is the transformation from the input state to the output state? In this case, theta does not change, and phi becomes pi plus phi. So what is this transformation? Well, it's in fact a rotation by 180 degrees about the z-axis. You can quickly verify and visualize this transformation using this block sphere by performing the rotation. Now we can do the same thing for the second case, for the second transformation, where we map from alpha beta to beta alpha. So what is the output state? Psi prime is e to the I phi sine theta over 2, which is beta, 0, plus alpha 1, which is cosine theta over 2, 1. Now we know we can multiply by a global phase to move this complex factor to the second term here. So we end up with sine theta over 2, 0, plus e to the minus I phi cosine theta over 2, 1. Okay, so what is this transformation? This time we map theta to pi minus theta so that cosine theta over 2 becomes sine theta over 2, and sine theta over 2 becomes cosine theta over 2, and phi becomes minus phi. And this, in fact, similarly, is a rotation about 180 degrees about the x-axis. Again, you can perform this rotation about x-axis to verify this process. Finally, if we look at the third example, this is the output state. And effectively, this is by setting theta to pi minus theta and phi to pi minus phi, resulting in a rotation of 180 degrees about the y-axis. So now we can reason about transformation of quantum state as rotations of the Bloch sphere. And in fact, we can represent this process mathematically with rotation matrices. For example, here, alpha minus beta is essentially a 2 by 2 matrix multiplied on the input. And we call this matrix the Pauli Z matrix for obvious reasons that it's a rotation about z-axis. And similarly here we have the Pauli X matrix. And here Pauli Y matrix. And in the quantum circuit notation, we can represent these three transformations as X gate, Y gate, and Z gate that transforms the input psi to output psi prime accordingly. These are in fact just special examples of rotation transformations, namely rotation by 180 degrees and about very nice axes like X, Y, and Z axis. What about arbitrary angle rotations? Well, we can also represent them as rotation matrices so that any quantum input quantum state alpha and beta will be transformed to some other quantum state, alpha prime, beta prime, that is rotated by gamma degree about the x-axis. Mathematically, we can write down the rotation matrix that accomplish this. And this matrix for rotation about x-axis can be written as e to the minus I gamma over 2 x. And this is the matrix exponential definition. For this case, in particular, we can write down a simpler looking term. In particular, we can perform this expansion because x squared is the identity matrix. Geometrically, we have rotated the entire Bloch sphere by gamma angle around the x-axis. Similarly, we can write down the rotation matrix for the y-axis as e to the minus I gamma over 2 times y, and do the same decomposition. And finally, for z-axis, again, visually, these gates are simply rotations of the Bloch sphere along different axes. And for a quantum program is then just compositions of these rotations. In particular, we can define a quantum program as just a sequence of quantum gates together with classical control flow. So let's take a look at an example written in the Qiskit language by IBM. We first define a quantum circuit of 1 qubit, and then a sequence of rotation gates is followed with different angles. And finally, we can draw the quantum circuit. As a result, you will see this quantum circuit notation where you start with input state psi 0, you apply Rx rotations, Rz rotation, and subsequently Ry rotation, and you will get a final state psi 1. More generally, these angles could be generated by a classical program, or you can even let a classical program to decide whether or not to perform a quantum gate. Later, when we talk about system optimizations, we will learn why in some cases we want to, for example, swap the order of quantum gates, merge two quantum gate into one, or even split one gate into several quantum gates, depending on requirements of the systems or optimizations. Now, in the last part of the lecture, we're going to look at one important step in system optimization, namely logic gate decomposition for single qubit gates. In particular, we want to achieve arbitrary rotation transformation using only standard rotations like Rx, Ry, or Rz. In particular, in this exercise, we're going to see that if we're given a system that can only perform Rx rotation by some angle theta and Rz rotation by some other angle theta, how can we accomplish arbitrary rotations by a composition of these standard rotations? For example, We start with this initial position for the Bloch sphere. And what we want to do is to rotate the Bloch sphere along the axis denoted as n hat by some angle. As a result, the Bloch sphere will end up in a position drawn on the bottom left. The best way to visualize how to accomplish this arbitrary rotation through only Rx and Rz rotations is by reversing this final position back to its original position. So let's look at the final position on the bottom left. How can we rotate the Bloch sphere from this final position into some position that's slightly nicer? And in this example, I'm going to rotate this final position of the Bloch sphere about the z-axis so that this north pole of the Bloch sphere is aligned with the YZ plane. As you can see, we have now rotated the north pole of the Bloch sphere around the z-axis so that the new north pole sits in the YZ plane. And next, we can rotate the Bloch sphere about the x-axis so it stays in the YZ plane, but now the north pole can align with my z-axis. Great, so now we have brought the north pole back to z-axis, its original position. All that's left to do is to rotate the Bloch sphere around z-axis so that all the points are aligned with our initial position over here. As a result, we have decomposed this transformation from the initial to final position with 3 steps by reversing what we have done. First, rotation, RZ rotation by theta 1. And second, Rx of some angle theta 2. And finally, Rz of some theta angle theta 3. Therefore, we have shown that arbitrary rotation can be written as a composition of Rz, Rx, and Rz.